second way of approximating integrals is Simpsons rule. So we've seen before with the trapezoidal rule that we can approximate the area under a curve here with a trapezium. We work out the area of this trapezium and hope if there's lots of strips that this is a good approximation. Well, for a single area here, we might, instead of using a trapezium, use a slightly different shape. What I'm going to do is I'm going to add a middle point here. As well as these endpoints, let's add a middle point. And what I'm going to do now is, instead of a straight line between these two endpoints, I'm going to actually form a curve between these 3 points. And it's actually a quadratic curve. So an equation actually of a quadratic here that I'm going to fit to these 3 points. Now, I'm not going to go through the full derivation of this, but it turns out that if I'm going to use this rule, what I need is an even number of strips. Here I've got 2 strips. Because I want that midpoint there, I need to have 2 strips. If I extend this to many strips, I will always need an even number of strips. Once I've got that, then I'm going to say that this point here is x1, x0, sorry, and this point here is xn, and then I'm going to split it up into lots of strips, remembering there's an even number of these, and then this next point is x1, x2, x3, all the way up to xn. Now I'm going to treat these slightly differently because the formula that comes out is slightly different from the trapezoidal rule. The formula says that this integral from a to b is approximately, and here I have to treat not just the end points differently, I have to treat the odd points and the even points different. So my formula now is h over 3, where h here is exactly the same as before. H is the width of each of these strips. It's b minus a divided by the number of strips. So h is the width of each strip. Now it's divided by 3, but then it's multiplied by the function evaluated at this endpoint plus the function evaluated at the other endpoint, this one here, and then 4 times the function evaluated at all the odd points. So x1, x3, x5, x7, etc. And finally, twice the function evaluated at the even points. Okay, so I need to work out all of these evaluations of the function, whatever that function is, and I put them into this final formula to calculate the approximate area. And this is Simpsons rule. Let's do an example of using Simpsons rule. Here I'm looking at this integral here, in fact the same integral I used for the trapezoidal rule, the integral of e to the x from x is 1 to x is 2. So a little diagram. Here's the function e to the x, and I want to work out the area between the curve and x is 1 and x is 2. Okay, so I'm again going to use 4 strips. It's not many strips, but I'm just going to use these 4 strips. I'm going to use the formula here. This is Simpsons rule. I need to work out my function at the endpoints at x0 and xn. And I've got to think about the function evaluated at the odd points. And then I've got to think about the function evaluated at the even points. Let's see what those points are. So if I've got x0, x1, x2, x3, and our final point will be x4, because we've got 4 strips, there are going to be 5 different points. Now what are these points? Well, the x0 is the very first point, it's x equals 1, and the very last one, x4, is x equals 2. The ones in between are going to be separated by a width h, where h here is b minus a over the number of strips, b being 2, a being 1, and the number of strips are 4. So that's a quarter. So each strip, each x point at the end of each strip adds a quarter. So these points here I can write down is 1.25, 1.5, 1.75, and then finally 2. The difference between these is just a quarter. And now I have to think about, for my formula, I need to think about the function evaluated at all these points. So what I'm going to work out is my function. I'm actually going to treat different points separately. So I'm going to look at the end points. I'm going to look at the odd points, x1 and x3. I'm going to look at the even points. So in fact, there's only one interior even point, x2. So what I'm going to do is work out the evaluation of my function, e to the x, at each of these values of x. So let's just do the endpoints. E to the 1, 2.718282. And then the other endpoint, x4, e to the value 2, e to the 2 is 7.389056. Then let's think about the odd ones. The odd ones are x1 and x3, they're the odd numbers, 1 and 3. I'll work out the exponential of 1.25 using my calculator. And for x3, the exponential of 1.75. And finally, what about the even points? There's only one even point, it's this x2. I work out the exponential of 1.5. And there we have it. So I have a column of endpoints, I've got a column of odd points, and a column of even points. There's only one of those for this case. What I'm going to do is I'm going to add each column up. That's exactly what I need for my formula. I need the endpoints added up, I need the odd points added up, I need the even points added up. So if I just add down the column there, this is what I get, 10.107338. Then I get 9.244946. There's only one even point, so add that to it just there, and it's 4.481689. These numbers here, these three numbers, are the numbers that go into my formula as these sums. The end points, the odd points, and the even points. So I put those numbers into my formula. Remember, I have to multiply the odd points, this sum here, by 4. I have to multiply the even points, this point here, by 2. I add them up. I multiply by h over 3. H in my case is a quarter. And I get the final answer. And my final answer is that my area is approximately 4.670875. And that's a pretty good approximation to the integral of e to the x from 1 to 2.